All right, anytime you want to graph a rational function, you can go through looking through these key features, and if you have these key features, you should be able to graph any function. So, one, look at the factors of the numerator. Why do I care about the factors of the numerator? Here's why. Let's say I have some number divided by some other number. Let's say it's, I don't know, 5x divided by 20x. Who cares? If I'm able to make the numerator equal 0, 0 divided by anything is 0. So the output of this entire thing right here is 0. The output of some x does this, which means that the output of that x is 0. So what numbers make that happen? What x's make that happen? So if I've got a quadratic in the numerator, if I factor it into its components and find those zeros, then that means that when x is a and when x is b, this entire thing must have an output of 0. So you can basically ignore the denominator when you're looking for the x-intercepts, which is when our function crosses along this axis. It may happen, it may never happen. In some instances, you won't even have an x-intercept. Okay. 2, I like to check and see if there is a y-intercept. Is it crossing the y-axis? So the parent function for reciprocals has no x-intercepts. It's just trying to have one. It's getting really, really, really close to x output of y equals 0, but you're not getting there. And then it has the same thing here. All right, no real y-intercepts. But if I had some transformation on my rational function, it might do something like that, where your asymptote is like there, and so it can cross. So there I'm going to have f of 0 equals some y-intercept. That's what we're doing there. And then 3, look at the factors of the denominator, because if I have a number over 0, what happens? The world explodes. Ah, big deal. So it doesn't matter what's in the numerator. If I'm somehow able to make either this quantity or this quantity equal 0, because this could be 12 on this side and this could be 0, and you're still blowing the world up. So if x equals some number a, so that if I have a minus a, I get 0, and or x equals b, right here, I get another number 0, you're going to get a vertical asymptote because the denominator can never equal 0. So let's say that a was 3 or something like that, and b were 2. So when x is 3, I take 3 minus 3, like that, and let's say this is negative 5 or 5. So 5 minus 5, so x can't be 5. So you've got a couple of vertical asymptotes here, and then, I don't know, maybe you had like a horizontal at 0 or something. I don't know, whatever. Horizontal asymptotes. Okay, that's the thing we just looked at, where you have the numerator is bigger, the denominator is smaller. Okay, this one you're going to have a slant, right? That's the weird one that we looked at on Desmos, where your rational function looks something like this. It's doing some weird thing like that. Or maybe it's trying to approach some line. Okay. And then you have where the numerator equals the denominator, and these are the power side. or the exponent size. And those ones will be A over B. So if these are the same, so if the exponent of the largest term of the numerator and the denominator are the same, then A over B is your horizontal asymptote. So let's say that this is the number A over B. And then we have where the numerator is smaller and the denominator is bigger. Again, flip back, play with that Desmos stuff. One will always approach 0. So maybe it's, let's say it's got a horizontal that way and a vertical this way. It's going to do, maybe it's also a -1. Say it does something like that. So this must have had, so it's -3 in the denominator, and maybe there's a 1, and then it's negative to flip the whole thing over. Oops, now you can see, sorry. Okay, this is just a review of those weird horizontal asymptotes, those weird ones that do the slant linear thing when the numerator is 1 larger than the denominator's largest power. So for example, if I had x squared plus 5x plus 4 over x plus 2, and x is going to approach infinity. Let's divide this term into every single thing. So this right here becomes x, because it doesn't really matter about that 2. As x gets infinitely large, this 2 is sort of irrelevant. It's like saying 1,000 squared over 1,000 plus 2. Well, it's almost 1,000. It doesn't really matter. So it's going to get really, really close to x. And then here, let's say I have 1,000 again as our input of x, or 1,000,000 or something like that. So 5,000,000 divided by 5,000,000 and 2, well, it's still just almost 5. So these are sort of an approximation, or what is it trying to do? So this becomes almost x, this becomes almost 5, and then if I take 4 and I divide it by something really, really big, like 1,000,000 again, so we're pretending that this is 1,000,000, then that's just basically 0. So we can ignore this last term. So that means that as x gets infinitely large, my graph is going to be trying really, really hard to reach out and touch the line x equals 5. So let's do it.